CIET NCERT presents audiobook Ganit Prakash, textbook of mathematics for grade 7.
Chapter number 6, Number Play, page number 127. On the right side of the page, there is a QR code provided, scanning which you can reach out to the additional resources. 6.1 Numbers tell us things. What do the numbers in the figure below tell us? Remember, the children from the grade 6 textbook of mathematics. Now, they call out numbers using a different rule. Here we have an image of children with numbers 0, 1, 0, 2, 2, 2 and 1. What do you think these numbers mean? The children rearrange themselves and each one says a number based on the new arrangement. Another image here of children having numbers are 0, 0, 1, 2, 2, 5, 6. Could you figure out what these numbers convey? Observe and try to find out. Page number 128. The rule is each child calls out the number of children in front of them who are taller than them. Check if the number each child says matches this rule in both the arrangements. Write down the number each child should say based on this rule for the arrangement given below. Here we have another image of 7 children in which you are supposed to fill up the numbers. Figure it out. Question number 1. Arrange the stick figure cutouts given at the end of the book or draw a height arrangement such that the sequence reads A 0, 1, 1, 2, 4, 1, 5. B 0, 0, 0, 0, 0, 0, 0. C 0, 1, 2, 3, 4, 5, 6. D 0, 1, 0, 1, 0, 1, 0. E 0, 1, 1, 1, 1, 1. F 0, 0, 0, 3, 3, 3. Question number 2. For each of the statements given here, think and identify if it is always true, only sometimes true, or never true. Share your reasoning. A. If a person says 0, then they are the tallest in the group. B. If a person is the tallest, then their number is 0. C. The first person's number is 0. D. If a person is not first or last in line, that is, if they are standing somewhere in between, then they cannot say 0. E. The person who calls out the largest number is the shortest. F. What is the largest number possible in a group of 8 people? Page number 129. 6.2 Picking Parity. Kishore has some number cards and is working on a puzzle. There are 5 boxes and each box should contain exactly one number card. The numbers in the boxes should sum to 30. Can you help him find a way to do it? Here there is an image in which some number cards are displayed having numbers 13 3 times, number 9 4 times, number 1 3 times, number 7 4 times, number 11 3 times, number 5 4 times and number 3 4 times. We are also provided with 5 boxes and there is a plus sign in between them that adds up to 30. Can you figure out which 5 cards add to 30? Is it possible? There are many ways of choosing 5 cards from this collection. Is there a way to find a solution without checking all possibilities? Let us find out. Add a few even numbers together. What kind of number do you get? Does it matter how many numbers are added? Any even number can be arranged in pairs without any leftovers. Some even numbers are displayed here arranged in pairs. In the picture, we can find there are 6 dots and then we have 10 dots displayed. Then 9 dots in pairs, that means 18 dots. As we observe in the figure, adding any number of even numbers will result in a number which can still be arranged in pairs without any leftovers. In other words, the sum will always be an even number. Here we have another image with 6 green dots and 4 blue dots. Now add a few odd numbers together. What kind of number do you get? Does it matter how many odd numbers are added? Odd numbers cannot be arranged in pairs. An odd number is one more than a collection of pairs. Some odd numbers are displayed here. Here we have an image of odd number dots. First one has 7 dots. The next one has 11 dots and another figure has 19 dots. Page number 130. Can we also think of an odd number as one less than a collection of pairs? This figure represents that the sum of two odd numbers must always be even. This, along with the other figures, here are more examples of a proof. Towards right, we have an image which has 7 green dots and 5 purple dots. There is also a cartoon displayed which reads out, we can see that two odd numbers added together can always be arranged in pairs. There's an image which has 3 green dots and 3 purple dots arranged to form a even pattern. Another picture has 5 green dots and 3 purple dots adding up to 8. There's another image which has 9 purple dots and 3 green dots. What about adding 3 odd numbers? Can the resulting sum be arranged in pairs? No. Explore what happens to the sum of A. 4 odd numbers, B. 5 odd numbers and C. 6 odd numbers. Let us go back to the puzzle Kishore was trying to solve. There are 5 empty boxes. That means he has an odd number of boxes. All the number cards contain odd numbers. They should add to 30, which is an even number. Since adding any 5 odd numbers will never result in an even number, Kishore cannot arrange these cards in the boxes to add up to 30. Two siblings, Martin and Maria, were born exactly 1 year apart. Today, they are celebrating their birthday. Maria exclaims that the sum of their ages is 112. Is this possible? Why or why not? As they were born 1 year apart, their ages will be two consecutive numbers. Can their ages be 51 and 52? 51 plus 52 is equal to 103. Try some other consecutive numbers and see if their sum is 112. The counting numbers 1, 2, 3, 4, 5 and so on alternate between even and odd numbers. In any two consecutive numbers, one will always be even and the other will always be odd. What would be the resulting sum of an even number and an odd number? We can see that their sum can't be arranged in pairs and thus will be an odd number. Page number 131. Since 112 is an even number and Martin's and Maria's ages are consecutive numbers, they cannot add up to 112. We use the word parity to denote the property of being even or odd. For instance, the parity of the sum of any two consecutive numbers is odd. Similarly, the parity of the sum of any two odd numbers is even. Figure it out. Question number 1. Using your understanding of the pictorial representation of odd and even numbers, find out the parity of the following sums. A. Sum of two even numbers and two odd numbers. Example, even plus odd plus odd. B. Sum of two odd numbers and three even numbers. C. Sum of 5 even numbers. D. Sum of 8 odd numbers. Question number 2. Lakpa has an odd number of 1 rupee coins, an odd number of 5 rupee coins and an even number of 10 rupees coins in his piggy bank. He calculated the total and got 205 rupees. Did he make a mistake? If he did, explain why. If he didn't, how many coins of each type could he have? Question number 3. We know that A. Even plus even is equal to even. B. Odd plus odd is equal to even. C. Even plus odd is equal to odd. Similarly, find out the parity for the scenarios given. D. Even minus even is equal to dash. E. Odd minus odd is equal to dash. F. Even minus odd is equal to dash. G. Odd minus even is equal to dash. Small squares in grids. In a 3 by 3 grid, there are 9 small squares, which is an odd number. Meanwhile, in a 3 by 4 grid, there are 12 small squares, which is an even number. Given the dimensions of a grid, can you tell the parity of the number of small squares without calculating the product? Here we have 3 by 4 grid, which is displayed here in a tabular column. Page number 132. Find the parity of the number of small squares in these grids. A. 27 into 13. B. 42 into 78. C. 135 into 654. Parity of expressions. Consider the algebraic expression 3n plus 4. For different values of n, the expression has different parity. Here we have a picture of a tabular column which has 3 columns displayed. First column represents n, second column represents value of 3n plus 4, third column represents parity of the value. In the first row, we have n as 3. In the second row, it is 8, and in the third row, it is 10. And the corresponding values in the second column are 13, 28, 34. And the parity in order are odd, even, even. Come up with an expression that always has even parity. Some examples are 100p and 48w minus 2. Try to find more. Come up with expressions that always have odd parity. Come up with other expressions like 3n plus 4, which could have either odd or even parity. The expression 6k plus 2 evaluates to 8, 14, 20 and so on for k is equal to 1, 2, 3 and so on. Many even numbers are missing. Are there expressions using which we can list all the even numbers? Hint provided here is all even numbers have a factor 2. Are there expressions using which we can list all odd numbers? We saw earlier how to express the nth term of the sequence of multiples of 4, where n is the letter number that denotes a position in the sequence. Example, first, 23rd, 100 and 17th, etc. What would be the nth term for multiples of 2? Or what is the nth even number? Let us consider odd numbers. What is the 100th odd number? To answer this question, consider the following question. Page number 133. What is the 100th even number? This is 2 into 100 is equal to 200. Does this help in finding the 100th odd number? Let us compare the sequence of evens and odds term by term. Even numbers 2, 4, 6, 8, 10, 12 and so on. Odd numbers 1, 3, 5, 7, 9, 11 and so on. We see that at any position the value at the odd number sequence is 1 less than that in the even number sequence. Thus, the 100th odd number is 200 minus 1, that is equal to 199. Write a formula to find the nth odd number. Let us first describe the method that we have learned to find the odd number at a given position. A. Find the even number at that position. This is 2 times the position number. B. Then subtract 1 from the even number. Writing this in expressions, we get A. 2n, B. 2n minus 1. Thus, 2n is the formula that gives the nth even number. and 2n minus 1 is the formula that gives the nth odd number. 6.3 Some explorations in grids. Observe this 3 by 3 grid. It is filled following a simple rule. Use numbers from 1 to 9 without repeating any of them. There are circled numbers outside the grid. We have an image of a grid which is 3 by 3 and their numbers displayed are 4, 7, 5 in the first row, 6, 1, 2 in the second row, 3, 9, 8 in the third row. Likewise, there is the total of the first row as 16 and in the second row the total adds up to 9 and in the third row the total is 20. Likewise, the total of the columns is also given. We have here for the first column total to be 13 and in the second column the total is 17 and in the third column we have total to be 15 which is displayed outside the grid. Are you able to see what the circled numbers represent? The numbers in the yellow circles are the sums of the corresponding rows and columns. Fill the grids given here based on the rule mentioned above. We have 3 by 3 grid and the first number in the first row is mentioned as 9 and there is one more number mentioned in the third row and third column, that is number 5. We also have the sums of the corresponding rows, like first row the total has to be 13, for the second row 14, for the third row the sum is 18, for the first column the total is 24, for the second column the total mentioned is 9 and for the third column the total is 12. Likewise, we have one more 3 by 3 grid with two numbers displayed, one in the second row. We have number 4 and one number is displayed in the third row, last box, that is 3. Similarly, we have the sums of the rows displayed as 24 for the first row, 15 for the second row, 6 for the third row. And the totals of the columns are, for the first column total is 12, for the second column it is 16 and for the third column it is 17. Page number 134. Make a couple of questions like this on your own and challenge your peers. Try solving the problem given here. You might have realized that it is not possible to find a solution for this grid. Why is this the case? Here we are given an empty grid 3 by 3 in which only one number in the second row and the third column is mentioned as 6. We are also given the sums of the rows as 5, 21 and 19 in first, second and third row respectively, and the sum of first column is 9, sum of second column is 11 and sum of third column is 26. The smallest sum possible is 6, that is equal to 1 plus 2 plus 3, and largest sum possible is 24, that is equal to 9 plus 8 plus 7. Clearly, any number in a circle cannot be less than 6 or greater than 24. The grid has sums 5 and 26. Therefore, this is impossible. In the earlier grids which we solved, Kishore noticed that the sum of all the numbers in the circles was always 90. Also, Vidya observed that the sum of the circled numbers for all three rows or for all three columns was always 45. Check if this is true in the previous grids you have solved. Here we have image of Vidya displaying that the three row sums added together gives 45. So does adding the column sums. Why should the row sums and column sums always add to 45? From this grid, we can see that all the row sums added together will be the same as the sum of the numbers 1 to 9. This can be seen as column sums as well. The sum of the numbers 1 to 9 is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 is equal to 45. Here we have 3 by 3 grid with the numbers filled in as follows. In the first row 4, 7, 5. In the second row 6, 1, 2. In the third row 3, 9, 8. And the total of the first row is displayed as 4 plus 7 plus 5. In the second row, the sum is displayed as 6 plus 1 plus 2. And in the third row, the sum is displayed as 3 plus 9 plus 8. Likewise, the sums of the columns are also displayed. In the first column, it is 4 plus 6 plus 3. In the second column, the sum is displayed as 7 plus 1 plus 9. In the third column, the sum is displayed as 5 plus 2 plus 8. A square grid of numbers is called a magic square if each row, each column, and each diagonal add up to the same number. This number is called the magic sum. Diagonals are given in the picture. Trying to create a magic square by randomly filling the grid with numbers may be difficult. This is because there are a large number of ways of filling a 3 by 3 grid using the numbers 1 to 9 without repetition. In fact, it can be found that there are exactly 3,62,880 such ways. Surprisingly, the number of ways to fill the grid can be found without listing all of them. We will observe in later years how to do this. Instead, we should proceed systematically to make a magic square. For this, let us ask ourselves some questions. Question number 1. What can the magic sum be? Can it be any number? Page number 135. Let us focus for the moment only on the row sums. We have seen that in a 3 by 3 grid with numbers 1 to 9, the total of row sums will always be 45. Since in a magic square the row sums are all equal and they add up to 45, they have to be 15 each. Thus, we have the following observation. Observation 1. In a magic square made using the numbers 1 to 9, the magic sum must be 15. Question number 2. What are the possible numbers that could occur at the center of a magic square? Let us consider the possibilities one by one. Can the central number be 9? If yes, then 8 must come in one of the other squares. For example, in this, we must have 8 plus 9 plus other number is equal to 15. But this is not possible. the same issue will occur no matter where we place 8. So, 9 cannot be at the center. Can the central number be 1? If yes, then 2 should come in one of the other squares. Here, we must have 2 plus 1 plus other number is equal to 15. But this is not possible because we are only using the numbers 1 to 9. The same issue will occur no matter where we place 1. So, 1 cannot be at the center either. On the right side, we are provided with 3 empty grids which are 3 by 3 grids. In the first one, we have 2 diagonal numbers mentioned, 8 and 9. The third diagonal number is missing. In the second grid, 3 by 3 grid, we have only 2 numbers mentioned in the column, that is 1 and 2 in the second row and the third row respectively. In the third 3 by 3 grid, only the center number 5 is displayed. Using such reasoning, find out which other numbers 1 to 9 cannot occur at the center. This exploration will lead us to the following interesting observation. Observation 2. The number occurring at the center of a magic square filled using 1 to 9 must be 5. Let us now observe where the smallest number 1 and the largest number 9 should come in a magic square. One second observation tells us that they will have to come in one of the boundary positions. Let us classify these positions into 2 categories. Here we have 2 3 by 3 grids in which in the first 3 by 3 grid only the corners are displayed with the dots, 4 dots, and in the second image we have dots displayed in the middle position in the first row and extreme positions in the second row and the middle position in the third row. Page number 136. Can 1 occur in a corner position? For example, can it be placed as follows? Here we have 3 by 3 grid in which diagonally 2 numbers 1 and 5 have been displayed and the total of the diagonal is represented as 15 and the sum of the first row is displayed as 15 and the sum of first column is also displayed as 15. If yes, then there should exist 3 ways of adding 1 with 2 other numbers to give 15. We have 1 plus 5 plus 9 is equal to 1 plus 6 plus 8 is equal to 15. Is any other combination possible? Similarly, can 9 be placed in the corner position? Observation 3. The numbers 1 and 9 cannot occur in any corner, so they should occur in one of the middle positions. Can you find the other possible positions for 1 and 9? Here we have 2 3 by 3 grids. In the first 3 by 3 grid, the numbers are displayed in the second row as 1, 5 and 9. And in the second grid, 3 by 3 grid, we have the number displayed in the second column as 1, 5, 9. Now, we have one full row or column of the magic square. Try completing it. Hint provided is, first fill the row or columns containing 1 and 9. Figure it out. Question number 1. How many different magic squares can be made using the numbers 1 to 9. Question number 2. Create a magic square using the numbers 2 to 10. What strategy would you use for this? Compare it with the magic squares made using 1 to 9. Question number 3. Take a magic square and A. Increase each number by 1. B. Double each number. In each case, is the resulting grid also a magic square? How do the magic sums change in each case? Question number 4. What other operations can be performed on a magic square to yield another magic square? Question number 5. Discuss ways of creating a magic square using any set of 9 consecutive numbers like 2 to 10, 3 to 11, 9 to 17, etc. Generalizing a 3 by 3 magic square. We can describe how the numbers within the magic square are related to each other. That is, the structure of the magic square. Page number 137. Choose any magic square that you have made so far using consecutive numbers. If m is the letter number of the number in the center, express how other numbers are related to m. How much more or less than m? Hint provided here is, remember how we described a 2 by 2 grid of a calendar month in the algebraic expression chapter. Here we have 3 by 3 grid in which the center box displays m. Once the generalized form is obtained, share your observation with the class. Figure it out. Question number 1. Using this generalized form, find a magic square if the center number is 25. Question number 2. What is the expression obtained by adding the 3 terms of any row, column, or diagonal? Question number 3. Write the result obtained by A. Adding 1 to every term in the generalized form. B. Doubling every term in the generalized form. Question number 4. Create a magic square whose magic sum is 60. Question number 5. Is it possible to get a magic square by filling 9 non-consecutive numbers? The first ever 4 by 4 magic square. The first ever recorded 4 by 4 magic square is found in a 10th century inscription at the Parshvanath Jain temple in Khajuraho, India, and is known as the Chautisa Yantra. We have an image of this Chautisa Yantra, and we also have 4 by 4 grid displaying the numbers as follows. First row 7, 12, 1, 14. Second row 2, 13, 8, 11. Third row 16, 3, 10, 5. Fourth row 9, 6, 15, 4. Below the image, it is mentioned that the first ever recorded 4 by 4 magic square, the Chautisa Yantra at Khajuraho, India. Chautis means 34. Why do you think they called it the Chautisa Yantra? Every row, column, and diagonal in this magic square adds up to 34. Can you find other patterns of 4 numbers in the square that adds up to 34? Page number 138. Magic squares in history and culture. The first magic square ever recorded, the Lo Shu Square, dates back over 2000 years to ancient China. The legend tells of a catastrophic flood on the Lo River, during which the gods sent a turtle to save the people. The turtle carried a 3 by 3 grid on its back with the numbers 1 to 9 arranged in a magical pattern. Magic squares were studied in different parts of the world at different points of time, including India, Japan, Central Asia, and Europe. Indian mathematicians have worked extensively on magic squares, describing general methods of constructing them. The work of Indian mathematicians was not just limited to 3 by 3 and 4 by 4 grids, which we considered here, but also extended to 5 by 5 and other larger square grids. We shall learn more about these in later grades. Here we have a picture of 3 by 3 grid in which the number displayed are as follows. In the first row 2, 7, 6. In the second row 9, 5, 1. In the third row 4, 3, 8. The occurrence of magic squares is not limited to scholarly mathematical works. They are found in many places in India. The picture to the right is of a 3 by 3 magic square found on a pillar in a temple in Palani, that is Tamil Nadu. The temple dates back to the 8th century CE. 3 by 3 magic squares can also be found in homes and shops in India. The Navagraha Yantra is one such example given below. On the right side of the page, there is a picture of turtle given with some dots displayed on it. We also have a picture of Navagraha Yantra displaying different planets: Mercury, Venus, Moon, Jupiter, Sun, Mars, Ketu, Saturn, Rahu. Page number 139. Notice that a different magic sum is associated with each graha. A picture of Kuber Yantra is given below. We have images of Kuber Yantra displayed here. Also, the 3 by 3 grid having numbers as follows. In first row 27, 20, 25. In the second row 22, 24, 26. In the third row 23, 28, 21. 6.4 Nature's favorite sequence. The Virahanka Fibonacci numbers. The sequence 1, 2, 3, 5, 8, 13, 21, 34 and so on. Virahanka Fibonacci numbers is one of the most celebrated sequences in all of mathematics. It occurs throughout the world of art, science and mathematics. Even though these numbers are found very frequently in science, it is remarkable that these numbers were first discovered in the context of art, specifically poetry. The Virahanka Fibonacci numbers thus provide a beautiful illustration of the close links between art, science and mathematics. Discovery of the Virahanka numbers. The Virahanka numbers first came up thousands of years ago in the works of Sanskrit and Prakrit linguistics in their study of poetry. In the poetry of many Indian languages, including Prakrit, Sanskrit, Marathi, Malayalam, Tamil, and Telugu, each syllable is classified as either long or short. A long syllable is pronounced for a longer duration than a short syllable. In fact, for exactly twice as long. When singing such a poem, a short syllable lasts one beat of time, and a long syllable lasts two beats of time. This leads to numerous mathematical questions, which the ancient poets in these languages considered extensively. A number of important mathematical discoveries were made in the process of asking and answering these questions about poetry. One of these particularly important questions was the following: how many rhythms are there with 8 beats consisting of short syllables, that is 1 beat, and long syllables, that is 2 beats? That is, in how many ways can one fill 8 beats with short and long syllables, where a short syllable takes 1 beat of time and a long syllable takes 2 beats of time? Page number 140. Here are some possibilities: long, 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 short, 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 long, long, short, long, 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 short, short, long, and so on. Can you find others? Phrased more mathematically, in how many different ways can one write a number, say 8, as the sum of ones and twos? For example, we have 8 is equal to 2 plus 2 plus 2 plus 2. 8 is equal to 1 plus 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 1. 8 is equal to 1 plus 2 plus 2 plus 1 plus 2. 8 is equal to 2 plus 2 plus 1 plus 1 plus 2, etc. Do you see other ways? Here are all the ways of writing each of the numbers 1, 2, 3 and 4 as the sum of ones and twos. Here there is an image of a tabular column which has 3 columns. In the second column we have different ways, and in the third column we have number of ways. And in the 4 rows we have the value of n's. In the first row, when n is equal to 1, different ways is 1 and number of ways is also 1. When n is equal to 2 in the second row, different ways are 1 plus 1, that is 2, and number of ways are 2. When n is equal to 3, the number of ways are 1 plus 1 plus 1, or 1 plus 2, or 2 plus 1. That is, number of ways in the third column displayed are 3. And when n is equal to 4, the different ways possible are 1 plus 1 plus 1 plus 1, or 1 plus 1 plus 2, or 1 plus 2 plus 1, or 2 plus 1 plus 1, or 2 plus 2. So, the number of ways displayed in third column are 5. Try writing the number 5 as a sum of ones and twos in all possible ways in your notebook. How many ways did you find? You should find 8 different ways. Can you figure out the answer without listing down all the possibilities? Can you try it for n is equal to 8? Here is a systematic way to write down all rhythms of short and long syllables having 5 beats. Write a 1 plus in front of all rhythms having 4 beats, and then a 2 plus in front of all rhythms having 3 beats. This gives us all the rhythms having 5 beats. Page number 141. We have another column displayed here with the value n is equal to 5, and the ways are represented in the second column as 1 plus 1 plus 1 plus 1 plus 1, or 1 plus 1 plus 1 plus 2, or 1 plus 1 plus 2 plus 1, or 1 plus 2 plus 1 plus 1, or 1 plus 2 plus 2. And the number of ways possible are displayed in third column as 2 plus 1 plus 1 plus 1, or 2 plus 1 plus 2, or 2 plus 2 plus 1. Thus, there are 8 rhythms having 5 beats. The reason this method works is that every 5 beat rhythm must begin with either a 1 plus or a 2 plus. If it begins with a 1 plus, then the remaining numbers must give a 4 beat rhythm, and we can write all those down. If it begins with a 2 plus, then the remaining number must give a 3 beat rhythm, and we can write all those down. Therefore, the number of 5 beat rhythms is the number of 4 beat rhythms plus the number of 3 beat rhythms. How many 6 beat rhythms are there? By the same reasoning, it will be the number of 5 beat rhythms plus the number of 4 beat rhythms, that is 8 plus 5 is equal to 13. Thus, there are 13 rhythms having 6 beats. Use the systematic method to write down all 6 beat rhythms, that is, write 6 as the sum of 1s and 2s in all possible ways. Did you get 13 ways? This beautiful method for counting all the rhythms of short syllables and long syllables having any given number of beats was first given by the great Prakritic scholar Virahanka around the year 700 CE. He gave his method in the form of a Prakrit poem. For this reason, the sequence 1, 2, 3, 5, 8, 13, 21, 34 and so on is known as Virahanka sequence, and the numbers in the sequence are known as the Virahanka numbers. Virahanka was the first known person in history to explicitly consider these important numbers and write down the rule for their formation. Other scholars in India also considered these numbers as the same poetic context. Virahanka was inspired by earlier work of the legendary Sanskrit scholar Pingla, who lived around 300 BCE. After Virahanka, these numbers were also written about by Gopala, that is c. 1135 CE, and then by Hemachandra c. 1150 CE. In the West, these numbers have been known as the Fibonacci numbers after the Italian mathematician who wrote about them in the year 1202 CE, about 500 years after Virahanka. As we can observe, Fibonacci was not first, nor the second, not even the third person to write about these numbers. Sometimes the term Virahanka Fibonacci numbers is used so that everyone understands what is being referred to. So, how many rhythms of short and long syllables are there having 8 beats? We simply take the 8th element of the Virahanka sequence 1, 2, 3, 5, 8, 13, 21, 34, 55. Thus, there are 34 rhythms having 8 beats. Page number 142. Write the next number in the sequence after 55. We have seen that the next number in the sequence is given by adding the two previous numbers. Check that this holds true for the numbers given above. The next number is 34 plus 55, that is equal to 89. Write the next three numbers in the sequence. 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, dash, dash, and so on. If you have to write one more number in the sequence above, can you tell whether it will be an odd number or an even number without adding the two previous numbers? What is the parity of each number in the sequence? Do you notice any pattern in the sequence of parities? Today, the Virahanka Fibonacci numbers form the basis of many mathematical and artistic theories, from poetry to drumming to visual arts and architecture to science. Perhaps the most stunning occurrences of these numbers are in nature. For example, the number of petals on a daisy is generally a Virahanka number. How many petals do you see on each of these given flowers? A daisy with 13 petals is displayed in the picture here, and also a daisy with 21 petals is displayed on this page, and there's one more daisy flower which has 34 petals. There are many other remarkable mathematical properties of the Virahanka Fibonacci numbers that we will observe later in mathematics as well as in other subjects. These numbers truly exemplify the close connections between art, science, and mathematics. There is a beautiful picture here of a musician playing tabla, and we have two cartoons displayed also. 6.5 digits in disguise. You have done arithmetic operations with numbers. How about doing the same with letters? Page number 143. In the calculations given here, digits are replaced by letters. Each letter stands for a particular digit between 0 to 9. You have to figure out which digit each letter stands for. We have a display of T plus T plus T as sum to UT. Here we have a one-digit number that, when added to itself twice, gives a two-digit sum. The units digit of the sum is the same as the single digit being added. What could U and T be? Can T be 2? Can it be 3? Once you explore, you will see that T is equal to 5 and UT is equal to 15. Let us look at one more example given on the right. We have K2 plus K2 as sum displayed as HMM. Here, K2 means that the number is a two-digit number having the digit 2 in the units place and K in the tens place. K2 is added to itself to give a three-digit sum HMM. What digit should the letter M correspond to? Both the tens place and the units place of the sum have the same digit. What about H? Can it be 2? Can it be 3? These types of questions can be interesting and fun to solve. Here are some more questions like this for you to try out. Find out what each letter stands for. Share how you thought about each question with your classmates. You may find some new approaches. We have a display of letters as YY plus Z is equal to ZOO and B5 plus 3D as sum ED5. KP plus KP adding up to PRR. C1 plus C adding the sum to 1FF. These types of questions are called cryptarithms or alphamatics. Figure it out. Question number 1. A light bulb is on. Dodgy toggles its switch 77 times. Will the bulb be on or off? Why? Page number 144. Question number 2. Liz Sweeney has a large old encyclopedia. When she opened it, several loose pages fell out of it. She counted 50 sheets in total, each printed on both sides. Can the sum of the page numbers of the loose sheets be 6000? Why or why not? Question number 3. Here is a 2 by 3 grid. For each row and column, the parity of the sum is written in the circle. E for even and O for odd. Fill the 6 boxes with 3 odd numbers O and 3 even numbers as E to satisfy the parity of the row and column sums. Here there is a picture of 2 by 3 grid which has a display of the parities as in the first row O and in the second row as E. Also, the disparity of columns is displayed as for the first column E, for the second column E, and for the third column it is O. Question number 4. Make a 3 by 3 magic square with 0 as the magic sum. All numbers cannot be 0. Use negative numbers as needed. Question number 5. Fill in the following blanks with odd or even. A. Sum of an odd number of even numbers is dash. B. Sum of an even number or odd numbers is dash. C. Sum of an even number of even numbers is dash. D. Sum of an odd number of odd numbers is dash. Question number 6. What is the parity of the sum of the numbers from 1 to 100? Question number 7. Two consecutive numbers in the Virahanka sequence are 987 and 1597. What are the next two numbers in the sequence? What are the previous two numbers in the sequence? Question number 8. Angan wants to climb an 8-step staircase. His playful rule is that he can take either 1 step or 2 steps at a time. For example, one of his paths is 1, 2, 2, 1, 2. In how many different ways can he reach the top? Question number 9. What is the parity of the 20th term of the Virahanka sequence? Question number 10. Identify the statements that are true. A. The expression 4m minus 1 always gives odd numbers. B. All even numbers can be expressed as 6j minus 4. C. Both expressions 2p plus 1 and 2q minus 1 describe all odd numbers. D. The expression 2f plus 3 gives both even and odd numbers. Question number 11. Solve this cryptarithm. ut plus ta gives the total as TAT. Page number 145. Summary. In this chapter, we have explored the following. First point, in the first activity, we observed how to represent information about how a sequence of numbers, example, height measures, is arranged without knowing the actual numbers. Second point, we learned the notion of parity, numbers that can be arranged in pairs, even numbers, and numbers that cannot be arranged in pairs, that is odd numbers. Point number 3. We learned how to determine the parity of sums and products. Point number 4. While exploring sums in grids, we could determine whether filling a grid is impossible by looking at the row and column sums. We extended this to construct magic squares. Point number 5. We saw how Virahanka numbers were first discovered in history through the arts. The Virahanka sequences 1, 2, 3, 5, 8, 13, 21, 34, 55 and so on. Point number 6. We became math detectives through cryptarithms where digits are replaced by letters. Here we have a picture of the cartoons displayed here. The first one reads, I just heard that 14,70,369 people got married last year. The second one reads, wait, shouldn't it be an even number? The eagle wonders with an exclamatory mark. Chapter 6 ends here.
Ganit Prakash, you were just listening to this audiobook, Textbook of Mathematics for Grade 7. Narration, Swarnlata Sharma. Sound recordist, Virendra Rawat. Production assistant, Soumya Malik. Directed and produced by Vimalesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.